a couple things about the exam. So the class average was in the 70s, somewhere around 75. I don't think it has to be that low. I don't think the average will be that low in the future. Um, I think, like if I had to guess, I would guess this is the biggest issue uh, that came up on the test was I sort of vaguely remember when I was in college, you'd be getting ready for a test, and the professor would give like a study guide for the test, and you'd sort of talk to your friends about like how much you trust the study guide, how much you have to be ready for something to be thrown out of left field at you. Um, so you should look at this exam, after class and go back and look at the practice problems and just notice how directly the skills that I asked you to develop doing those practice problems transferred to these. You know what I mean? Like there are triangular distributed loads, there's a parabolic distributed load, there's a compound, centroid problem where you have to break it up into sums of rectangles. There's almost an identical friction problem, you know. So so really, I think people just didn't focus on the practice problems as much as you should have. Like if you if you do nothing else, you just go through the notes enough that you can make a good attempt at the practice problems. Then you do the practice problems once, go to the solution, see what you did right and wrong, or even if you have questions about it, bring bring your attempt at the practice problems to my office hours, and we can go through it, and I can tell you what was good and what is wrong. Um, and then later go through those problems another time, go through the solutions. Every single skill that you're going to see on the exam is on those practice problems. Okay? So I don't know. Like that's what my guess is, that was the biggest thing. Like people just didn't really know what to expect, and maybe I should have clarified that a little more. But now you know what to expect. Okay? It's like um, so it's like you're standing up at the plate and in a uh, baseball match. What do they call it? Like you're on the 50-yard line of a baseball match. No, and the pitcher's like, "Are you ready? I'm going to throw you a fastball." And you're sort of like in the back of your mind, you're like, "Is he messing with me?" Like I better be ready for a curveball. And then, so I'm telling you, I told you to expect a fastball. I sort of got the sense a lot of you were looking for something else, but it's going to be all fastballs. You just have to do these practice problems. Okay? Um, and then there were two specific things um, that I saw over and over again that I just want to clarify. They're not like the biggest issues on the exam, but they're just two things that I saw a lot. Um, the first one is on that friction problem. You don't have to use a dot product on that problem. There are a couple ways to do it. But if you use a dot product, a dot product is also known by the name scalar product. And there's a reason for that. It's because when you take a dot product, you get a scalar. So like if you have AB dotted with CD, that's equal to AC plus BD. Okay. What I saw more than twice is people going AC BD. Okay, getting a vector answer. That actually is not. even though that sort of seems like a sensible way to multiply vectors, that doesn't end up, it turns out that's not a useful way to multiply vectors for anything. So never do this. If you're going to take a dot product and you don't get a scalar out, you did something wrong. And then the second thing was vector notation. Say something like this. That over arrow means, like, I don't know if I'd call this a definition of what a vector is, but I think this is a good way to think of it. Anything that has this over arrow over it means you can break it up into components. So don't write this. Don't write this vector f is equal to fx, fy, where the components have vector notation, right? Because we're all the way at the lowest level at this point. You know what I mean? Like there's no components inside these components. Okay? So when you're talking about vector components, you should write those as this indicates that those components are scalar variables. And that's what they should be, right? You have a vector whose components are scalars. And this is how you indicate that. So when you use these components in equations or whatever, they shouldn't have arrows over them. Okay? This is just, I mean, I think it's useful in making it clear to yourself what you're writing about. And then it's also useful in the sort of dirty little secret of engineering and math and physics. And that is that if you write stuff down the right way, people think you're smarter. Okay? So this is an easy way to look smarter. Okay? And some of you really, really need that. Anybody have any questions about the exam? There were good scores. There was sort of a spread throughout the whole spectrum. It was a pretty normal looking distribution, bell curve distribution. There were 4 or 5 24s. But then I think it'll be easy for, not easy, but like you have to do these problems and stuff. But I think it'll be pretty straightforward for us to see the class average go from 75 to 85, and that's more what I'd like, you know. Like when I gave this test out, I was sort of thinking there might be a chance that half the class would get A's on it or something, you know. And I don't think that's unrealistic. Like unrealistic. It's not impossible. It might be slightly optimistic, but like this class is just about it's really just about a couple of things, you know. It's being able to do free body diagrams well, really knowing how to apply Newton's second and third law, and if everybody in the class develops those skills, and I know each individual person could develop those skills, then I'll give out 40 A's, you know, and I'll get fired, and I'll work at McDonald's. They don't really fire you for giving 40 A's. I don't think. I've never done it. You could always say. Yeah. And also, so if the scores do stay low, and I start to get the sense that it has more to do with my expectations or something, like I'm open to curving the class, you know, curving things, but I don't really think we're going to have to. I don't think it's probably going to require that. You just have to get ready to hit fastballs, okay? Just get in that batting cage and hit fastballs. That's how to get ready. Okay? Okay, any questions on any of the individual problems? You want to see how, like, curious about how to do any of those, or?
Will you post solutions?
I can post solutions. Yeah, maybe I'll just do that. A couple of people did the, I don't know, like, maybe 5 people or something fell back into their old little physics trap on that first problem of setting their coordinate system like this. And I even saw, which is fine, that's a good way to do that problem, but that wasn't what I was trying to get at here. A few people even calculated like coefficients of friction and stuff, which I didn't ask for, but so yeah, like a few people, I mean, that just said to me that, like, since there was a problem on the practice problems that was, I think, an exact mirror image of this problem, that just said that a lot of people hadn't, hadn't done that, at least that specific practice problem to the, in the detail that you need to do these practice problems. All right, enough of that. So today I'm going to finish talking about structures. And the way that I am going to finish talking about it is by, like, you might ask, hey, Mr. Lakin. Like, that's supposed to be that guy from, I never even watched this show, so I don't really know what he sounds like, but the guy from Welcome Back, Kotter. Mr. Lakin, how come the way we did structures for 2 weeks in this class is not the least bit like what they do in the book? Doesn't that seem a little weird? So that's what I'm going to talk about, like why the book just approaches structures in a totally different way. I'm going to do one example problem. I'll tell you the benefits of how they do it, and I'll tell you why we did it a different way. And basically, I mean, the basic answer, I'll give away the punchline, is that the way they did it was a really good way to do it in 1952, when computers were things in science fiction novels. Okay, so I'm going to call this simplified methods for structures. And they give you in the book, this is chapter 5 of the book, 6 in the book. They give you 2 simplified methods for 2 different types of structures. So they break up structures into different subcategories. And their subcategories are trusses and frames. And again, sort of giving away the punchline, you should keep in mind that trusses and frames are not, there's more in structures. You need more subcategories to make up all of structures than just trusses and frames, okay? So there are types of structures that the book doesn't tell you how to solve, okay? And that's why, I mean, that's the main reason why I gave you the method I gave you. That general method solves everything. Trusses and frames give you a slightly easier way to solve some subsets of all structures. So first, trusses. Here's what a truss is. it's a set of members connected by pins. So I guess I'm going to number sort of the things that are required to fit into this category of trusses, so you can use the method in the book. So these members are connected by pins. The weights of the members are neglected. And all loads on the structure are applied at the pins. And if any of these conditions aren't met, then this thing, you can't use the method in the book. Okay? So I mean, that's a pretty strong set of requirements. This whole method that half of chapter 6 in the book is spent on, just decide that you want to take the members' weights into account and you can't use it, you know, or decide you want to apply a load at the midpoint of a member, you can't use it. So here's an example of a truss. And I think this is the example I'm going to solve. So that's a pair of rollers there on that side. Okay, if you, right now, assuming, you know, assuming these conditions are met for this truss, what are the loads in each of those members? Who can do that in their head? Weights neglected. Yes. Thank you. 0 loads. So we got to apply something, because 0 weight, you know. So nothing's applying forces to anything. So I'm just trying to see who's awake. One person. That's better than average. Okay, so we'll apply a load at that pin. And the simplification that we make, if all these conditions are met, like what can we do to make this problem simpler, to reduce the number of equations? Because that's what I mean by simplified. We're just going to have fewer variables and fewer equations needed to solve it. So if those conditions are met, the simplification comes from the fact that every member is just a two-force body. And that means that that the forces along each of those members have to be along that line between the pins, right? That's a requirement, or a fact about two-force bodies. So the forces on each member are along a line between the pins. If you lose any one of these 3 conditions, then you don't have two-force bodies, and that's why this doesn't translate to any other types of problems. Okay. The second, so this was trusses. The second type of structure that is dealt with in chapter 6 is frames. And the requirements for frames, there are also 3 conditions that have to be met for this to meet the book's definition of a frame. The members first have to be connected by pin joints. Second, only 2 members can connect at any given joint. And third, the loads have to be applied to the members themselves and not to the pins. Okay, so you can see that these are different sets of requirements. Frames, you can deal with weights for the individual members. That doesn't like exclude a structure from this treatment. A frame at any given joint can only have 2 members connected. That wasn't the case with trusses. Like look at this joint here. There's 1, 2, 3, 4 members connected at that pin. A frame can't have that. And third, on these frames, the loads have to be applied to the members themselves, not at the pin joints. Like this is applied to the pin. An example of a frame would be something like this. So these are all pin joints. This doesn't have to be a pin joint, by the way. That's a fixed joint in my example. But notice at any one of these joints, unlike the truss that I drew, at any joint there's only 2 members connected. Okay. The simplification comes from the fact that there are only 2 members connected at each joint. And I'll say at each joint A. So one member has a force applied on it that we can call FA, and the other one has a force applied to it, negative FA. Okay. And so we can talk, because of this set of conditions, we can talk about joint forces, you know, the joint force FA. And actually, this method, it makes bookkeeping a little simpler than the way we talked about it. But for the most part, this is fundamentally the method that I gave you for general conditions. And there are some things that make this method in the book a little easier, but I'm not going to go into that because it's similar enough to our method that I don't think there's much point in going into it. But I do want to just do one example of a truss problem, so you can see how much this method reduces the number of variables, reduces the number of equations, and you can see how it all works. And actually, the simplification that you use in a truss is something you can apply whenever you can apply it to any individual member of a structure that is a 2-force body. Okay. So let's do this example, okay? The one I drew here. And I'll say that these are all equilateral triangles and all the lengths are 1 meter. Makes the math pretty easy. So 1 meter, and then all these angles are the same. So the first thing we're going to have to do to solve this truss is label all the joints and label all the members. So I'll say A, B, why is B over there? Who knows? C, D, E. This is literally the craziest lettering system I ever put together in my life. And then number the members. 1, 2, 3, 4, 5, 6, 7. Okay. So the first step is the same first step that we do with our general method. We're going to isolate the whole structure, the whole truss, and see what we can figure out about the reaction loads. So the free body diagram looks something like this. There's the 50,000 Newton force. And what kind of forces are acting on the whole truss at A? Force vector, yep, right. So I'll call that the force FA. And what's acting at B? Yep. So that's just a force perpendicular to the surface of contact. I'll call that force FB, and that's just a scalar. And since these are all, we're going to see that everything's vertical. Like if this doesn't occur to you as something you can simplify immediately, that doesn't matter. Just write out the whole table. But I'm just going to go straight to Newton's second law and the rotational equation. So we have FAX, FAY, plus 0 FB, that's this force, plus 0 negative 50,000 is equal to 0, 0. And then the rotational equation, I'll calculate it about A. So there's no moment due to this. The moment arm for that 50,000 Newton force is 1.5. And that's going to produce a clockwise rotation. So that's a negative moment of 75,000. And then this moment arm for this force FB is 2. So 2 FB equals 0. And you can solve this for those three variables. You get FB is equal to 37,500, and the vector FA is equal to 0, 12,500. So far we haven't done anything different than we do using our method. Now the big simplification comes. And you know, if you're looking for sort of practice to clarify some of these ideas, here's one thing that is, I think, sort of interesting and clears something up for you. Try setting this problem up as a system of equations using the general method and see how many equations you get. You know, it's a huge number, right? A truss like this big would be a very big system of equations you have to solve. That doesn't make it hard, but it makes it tedious, and especially back when people had to do a lot of these calculations by hand, it makes it something you want to avoid. With this specific truss method, we're going to get a real limited number of variables and equations. Okay, so now what we're going to do is we're going to go joint by joint. And since we know these are two force members, right? We know that those members have forces applied along the line between the joints. By Newton's third law, that means that we can assume that the joints have forces acting in the directions along the members, right? That's just Newton's third law. And so we're just going to go joint by joint, and since each pin joint is, we can think of it as a particle, we're only going to use Newton's second law. We're not going to use the rotational equation at those pin joints, okay? So for every pin joint, we can get two equations, and the only variables we have are, we can represent the force in a member as a single scalar. We know the direction. It has to act along the line of the member. So let's go to a free body diagram of A. What forces are acting on that joint A? Well, we have this force FA, right, coming from the pin, or from the ground, however you want to think about it. And we already know the magnitude of that, 12,500. And then we're going to assume that every member is in tension. So if we get a positive value for the tension, it'll mean we were right, that member is in tension. If we get a negative value, it'll mean it's in compression. Because we know these forces are acting along that line, the question is just whether they're acting this way along the line or this way, okay? So if the members are in tension, so say that this member 3 is in tension, which direction is it going to pull on that pin A? Right, exactly. So we'll have a force that I'll call F3, because that's the force applied by member 3. And what direction is this member 1 going to apply at that pin? The right, yep. And those are the only loads acting on that pin. So Newton's second law says, and you have to do some stuff with unit vectors, but we have 0.5 F3, 0.866 F3. I say unit vectors, but in this case, you're just using sine and using trig to calculate what those are. But remember, like when you use sine and cosine, that's what you're doing, is calculating unit vectors. Plus F10 plus 0, 12,500 is equal to 0, 0. And here again, we can solve for these variables as we go. You can't always do that, but sometimes you can. F3 is equal to negative 14,434.2. F1 is equal to 7217.09. Since F3, we got a negative answer, that means this is in compression. F1, since we got a positive value, that means it's in tension. And now we'll go on to free body diagram of B. At B, we have a 37,500 Newton force acting up. Then we have the force due to member 7 that's acting. We're assuming, again, it's in tension, so this time it's going to be acting up and to the left, right? So we have F7. And then we have F2 acting to the left. So we have, for Newton's second law, negative 0.5, 0.866, F7 plus negative F2, 0, plus 0, 37,500 is equal to 0, 0. And we can solve this one too. We get F7 is equal to negative 43,302, and F2 is equal to 21,651.3. So what do we still need? We're just trying to find the forces in each of these members, right? Now we have 1 and 3, 2 and 7. We need 4, 5, and 6. So let's do a free body diagram of joint D. Okay, that'll have a lot of those in it. And what loads are acting at D? We have a force F1. So remember, F1 at A, we're assuming it's in tension. So F1 at A was pulling to the right. Now, again, we're assuming it's in tension, but this time that same member is pulling this joint to the left, right? If it's in tension, it's trying to pull those two joints together, right? So we have this force due to F1, and our force F1 was, where is that? 7217.2. Okay, thanks. 7217.09. I think that one was positive. F3 is the one that's, and then going the other way. So yeah, it would be negative, but I put the arrow going that way. And then going this way, we have the force F2. That's 21,651.3. Yeah. And then we have a force F4 pulling that way, and a force F6 pulling this way. So Newton's second law says negative 7217.09 plus 21,651.30 plus 0.5 F6 0.866 F6 plus negative 0.5 F4, 0.866 F4 is equal to 0, 0. And again, two equations, two unknowns, so we can keep just solving these as we go. No, we can't, can we? We should be able to. Yeah. So we get F6. This time, I guess you can't solve, like there isn't one equation that tells you one. You have to solve it as a system. But you get that F4 is equal to 14,434.2, and F6 is equal to negative 14,434.2. So member 4 is in tension, member 6 is in compression. And now there's only one. We've solved for every variable that we've come across so far. There's only one variable we still don't know. We don't know the force in 5. So we need to pick one of these joints that 5 is connected to. Okay, I'll pick C. So Newton's second law for C. We have the force due to 3, the force due to 4, and the force due to 5. Those are the only forces. If I'd done this one, we'd also have to add that 50,000. So F3 is going to be pulling down this way, F4 this way, F5 this way. So we have F4, which we just... Oh, F3 this way is negative 14,434.2. So notice I kept drawing the arrow in that same direction indicating tension, and then used the negative sign from our answer. Okay. Then we have F4 here, positive 14,434.2, and then F5. And Newton's second law says this one, 0.5, negative 0.5 times that magnitude. Negative 0.866 times that magnitude. And then 0.5 times this magnitude, 14,434.2, negative 0.866, and then plus F5, 0 is equal to 0, 0. And we only need one of these two equations, right? Because we're just trying to solve for one variable. I guess it only appears in one of them anyways. So we'll take this one, and we get F5 is equal to 14,432.2. So F5 is in tension. Okay, and just like that, we solved that whole truss, which would be really a mess to solve using that general method. But like theoretically or whatever, it's no different than solving any other structure problem. Um, and then the way you'd use this, so trusses, the most obvious place you see trusses in engineering designs is in bridges. So say you're building a bridge, and so you design this truss, um, you plan on that certain type of loading, and you want to know where this bridge is in danger of failure, or possibly where you have to put um, your stronger members in putting this bridge together, right? So now here's how you use the information we just got. What's happening at um, member one? There's this relatively, compared to the other forces, small tension force. We're not too worried about it. Members 3 and 4 and 5 and 6, some are in compression, some are in tension, but those forces are like twice as big as member 1, but there's still bigger ones, so those aren't our main concern. But then you see that members 2 and especially member 7 have these big loads, right? So you'd look at this design and say, member 7, right here, I'm concerned that that's going to fail in compression. That's going to collapse, okay? And member 2, I'm concerned that that's going to fail in tension. It's going to stretch, elongate. And that's how you'd use this information. But of course, you can get that same information from the general method. It just isn't quite as like concise or easy, quick to solve.
Now, is it again for the trust method, you have to assume that the force is being applied at a pin?
Yep.
Right, so like if you were gonna say like how much weight can the bridge hold, you can only do that if you're applying forces, like say at the pins.
That's
along the
true.
way.
That is true.
Does that affect at all, like the calculation? Like say if instead you're worried about, well, what if the bridge fails like in the middle of the member because
Right.
does that
Um,
change the analysis at all, or will it ultimately result?
usually, usually in a truss, you wouldn't be worried about that because the next thing we're going to talk about is internal loads, and we'll see that if you have a two-force member, the internal loads are the same everywhere. So, so just knowing what those tension or compression values are already tells you everything about those internal loads. They're the same everywhere. So you wouldn't worry about that specifically. But I suppose you might worry like, so how is the bridge loaded? But I guess you would build the truss. You'd lay something on top of it that would be loading a bunch of those pins at once. You know what I mean? And so you do this analysis of the truss. You'd combine that with an analysis of the beam that's laid over the top, which is actually a plate, but if you're doing it in 2 dimensions like that. So yeah, I think it works pretty well. And I don't know much about the civil engineering they do to design a bridge, but I wouldn't be surprised if just that simple truss analysis is still used for some areas of looking at bridge design. Mm-hmm. So yeah, so like, are you talking about like the benefit of this simplified method versus? Mm-hmm. Yeah. Yeah, right. It's just um, when you're writing a computer program to do a physics problem, like to me, in my experience, the biggest thing you need in order to program something, it isn't how long the problem is. That doesn't have it. Like the computer deals with the length of the problem. You as the writer just have to come up with an algorithm for it. So what you need is a real systematic way to do the problem. You know what I mean? And then you just get the computer to loop over a billion pieces or whatever, while you go drink coffee, you know? So, so as a computer programmer, that general method doesn't have really any disadvantages over the truss method, you know? because it is a little harder work for the number cruncher, but the computer's the number cruncher. You know what I mean? It's just the systematic nature of it that you need in order to program it. Okay, so this was quicker than it would have been with the general method. Especially if you're on general meth. So why did I teach the general method? Yeah, that's the biggest thing. You only have to learn one thing. You don't have to learn a whole bunch of different approaches for a whole bunch of different types of problems. So first, one approach is better than 2, and I'll say 2 plus because that still doesn't, those 2 methods that they teach in the book still don't give us all the power of the one general method. 2, in practice, you wouldn't solve this by hand. So the benefits of that truss method, so like, what do I mean by in practice? I mean, if you're in a position where you have to get a right answer, okay? You wouldn't solve it by hand because you just make too many mistakes by hand, It's just, I mean, I suppose you could do it by hand 4 different times or something. And if you get the same answer all 4 times, you could be pretty confident. But for the most part, especially if you have even a moderately complicated problem, you're going to write a computer program for this because you just don't trust your own calculations. And like I said, I mean, that was a really important question about well, someone still has to write the computer program, so it's simpler for the person writing the computer program. But that's not like exactly true. Programming the general method isn't any more tedious than programming the truss method. And the third thing is, of course, what about this problem, or a million other ones that you could come up with easily? Like, we just changed one tiny detail about this, and now we can't solve it, or we have to come up with a whole nother approach to solve it. So with the method that we did, you can solve any collection of bodies you can put together with joints you can solve, and that's worth a lot of extra calculating. Okay, anyone have any questions about? Yep.
On that one, could you use the general method just to solve like that middle triangle, find the reaction as long as those joints, and then use the truss method?
Yeah, how would you do it? You're definitely onto something. That might not be exactly the way you do it. I'd have to think about that. But what you could do is all of these that are 2 force members, when you isolate, say like when you isolate this member, just treat it like you have forces F1 acting in known directions. Okay, so that's how you use the sort of the spirit of that truss method to simplify the general method. Okay, so now instead of what would have been 4 unknowns, we have 1 unknown, and it cuts down the number of equations you need a lot. So if any of you are working on problems and you see a 2-force member and you can't figure out how to use that, you want to talk to me about it, come by my office or talk to me after class and I can help you with that. Any other questions on this truss method? Okay, that's the end of structures, but we're going to keep doing structures problems. Like, I'm pretty much going to keep presenting all the problems through structures problems. The next thing we're going to do is talk about internal loads. And so I'm going to still give you structures and we're going to calculate internal loads in the members.